So now what we're going to do is have a look at some of the reactions that benzene can undergo, such as Friedel-Crafts acylation and nitration. However, what's first important is that we look at the actual just general mechanism of electrophilic substitution and understand how that works. For greater understanding of the structure and bonding of benzene, that will be in a completely different video, so we won't go through that now. But what we do know is that benzene has a ring of delocalized electrons. Electrons are negatively charged, which makes this ring very, very negative. As a result, it's not going to readily be attacked or attack a nucleophile, because the lone pair on the nucleophile would repel the delocalized ring. But what does happen is that ring of electrons can attack an electrophile. I'm just using E for now, as it's just a generic mechanism. So an electrophile, we know, is an electron pair acceptor. So what it's able to do is accept electrons from the ring. So those delocalized ring of electrons will be attracted to the electrophile and therefore attack it. Arrows show movement of electrons, so they're showing movement from the ring towards the electrophile. What makes benzene super stable is the fact that it has a ring. By attacking that electrophile, we're somehow adding the electrophile to the ring, which it's not overly happy about. So what does happen is we form a ring that's now positively charged, because some of the electrons in the ring have now bonded to the electrophile and formed a covalent bond. It's currently existing in this really unhappy intermediate state. So in order to remake stability, in order to go back to its high stability area that it likes to kind of sit in, sorry, that didn't make sense. In order to go back to being very stable, it needs to reform the ring. We've just added the electrophile, so really I don't want to lose it again. But what does happen is that electrophile actually will substitute the hydrogen. So the electrons in the carbon to hydrogen bond, both of them move back into the ring. So now what we've done is reformed the ring of electrons and substituted an electrophile onto the ring. This mechanism is worth 3 marks. The first mark is to show the attack from the delocalized ring towards the electrophile, and the second mark is for the intermediate. A couple of things to be mindful of for the intermediate. Firstly, when we draw that horseshoe structure, it has to be on the carbon, it has to go from the carbons on either side of where I'm adding the electrophile. So if I'm putting the electrophile here, then the horseshoe has to span over there. If I'm putting the electrophile over here, the horseshoe would have to span, or start from here and end here. If I have the electrophile at the top, the horseshoe starts here and will span all the way around to here. If we draw the horseshoe beyond or not far enough, we lose the intermediate mark. We also, within that intermediate mark, have to put our positive charge in the ring and show the electrophile and the hydrogen. Your third mark then finally is for showing the electrons from that carbon to hydrogen bond going back into the ring. You don't get any marks for showing your product, however it's good practice to always do so. So that's just a recap of electrophilic substitution.